Hello and welcome to PyData Global 2021. My name is Marisha Winkels and I am very happy to be here and be your host for this keynote session. I would like to now welcome David Beazley. You may know David as the author of the Python Cookbook, the Python Essential Reference, or the recently published Python Distilled. He is currently an independent researcher and educator who teaches advanced computer science courses, which you can find on his website. In today's keynote, and he will take us through a first-hand oral history from the earliest days of Python in science and answer the question, how did we end up here? At the end, we have approximately 10 minutes for Q&A, so please feel free to ask David your questions throughout the talk. David, the floor is all yours.
Okay, thank you very much. Glad to be here. Kind of a mysterious title, begin, end, but the topic of this talk is really why Python? Like, why did Python, of all things, take over the world of science? That's a question that a lot of people ask, especially computer scientists actually like to ask this question a lot. Like, how did this happen? And who let this happen? Because sometimes they look at Python and just like, it's a very unlikely story, right? A language named after Monty Python and developed on the side, all this stuff. How did it take over science? And a common answer that is sort of given for this is that people use Python because of the tools, NumPy, SciPy, pandas, matplotlib, and all that. But where did that stuff come from? I mean, that's an answer now, why Python has become popular. But what happened before that? How do things begin? And in some sense, this talk is a story about that. It is a personal story for me. It is not the only story, but I think it gives some kind of insight into what people were thinking and what was going on in kind of the earliest days of Python and science. So to start this off, I'm gonna time warp to 1994, and I'm gonna talk about lightning strike. And in 1994, if you were really into scientific visualization, you might have had a Silicon Graphics workstation. This is a Silicon Graphics Crimson. It's about a $75,000 machine, not cheap, but this was the thing to have on your desk. I mean, this was great. And so it was a little bit unfortunate when ours got blown up in a lightning storm one day. And so it got struck by lightning. And honestly, I was kind of happy about that. I was like, good. I'm glad it got struck by lightning. Now you're looking at that, Dave, you've got some kind of attitude problem. I mean, what's with you and not like wishing harm on this machine? I mean, this is the machine to have. This was Jurassic Park. It was in the movie. There it is. It's like in the movie, the Silicon Graphics workstation. It was the thing that the girl used to fly around Unix. If you know the movie, it's like, yeah, I know Unix. This is great. So why would you want harm on it? And so we had one of these machines. This is our office. The machine was actually sitting over there in the corner. I didn't realize 25 years ago that this photograph would be used in a conference. So it's not a very good picture of the Silicon Graphics, but Neil sort of sat over there. And I sat here on the Sun workstation. Okay, so you might think, oh, okay, Dave's just envious. Got the Sun, he doesn't have the Silicon Graphics. So this is kind of the setup. This was our fine facility, this trailer off the side of the road. Like looking at that, it's like, huh. Lightning struck out in the parking lot. I actually remember the lightning strike because we were trying to meet a paper deadline that day, and lightning struck the parking lot. And it just so happened that all the network cables for the machines in the building were actually sitting on the ground, literally on the ground underneath this trailer, and they sucked up the lightning bolt, blew out all the network interfaces. So it's like, okay, well, that was unfortunate. And then you can also look at this and just say, what kind of dump is this? Like, where's the guy working? In a trailer? What looks behind like a garbage incinerator or something? Where is this? So we're kind of over here. They don't even want to show us on the picture of the place, but the rest of the laboratory is up on a mountaintop here. This is a big government facility, Department of Energy, big facility. I actually spent most of my time interacting with the Beast, which was located in that building that I have highlighted there. Now, a lot of my day-to-day time was spent interacting with the Beast, basically. Okay, so you have the Beast. I would submit batch jobs to the Beast. And then the beast would run for 3 to 6 hours or something like that and produce a bunch of data files. As it turns out, you can only schedule about 6 hours on the beast at a time, because then other people would want to use the beast. And it's like, so you would kind of schedule batch jobs on that, produce a lot of data. I would then take all those data files and FTP them over to my Sun workstation over a 10 megabit connection maybe, and then try to store them on my local disk, which was not very big. I mean, you look at these numbers, keep in mind this is 1993. Okay, so like 4 gigabytes in 1993 was still a lot of space. So, but it's transferring data, not a lot of space. I then have to fight Niels over that SGI. He's a postdoc, and I'm like, okay, so we get in some battle where I'd use his machine. I have to relocate over there. And then after a few hours or days of fooling around, I would get some nice pictures and then kind of repeat the process. Kind of painful, to be honest. Not the smoothest workflow, but you did get some nice pictures out of it like that. I even have the picture here. I can fly it across the Zoom. It's like a special effect. It's like, okay, so you get some nice pictures out of the thing. You might get a magazine cover out of it. And if you're really, really lucky, maybe you'd even get on the news or something. It's like, oh, CBN News. So there's some picture I rendered on that SGI that ended up on the news. So it was really pretty, but it kind of was terrible, to be honest. I mean, I was really glad when the machine got struck by lightning. It was like, good, you deserved it, because it's like this workflow is like terrible. Okay. Now, part of the problem here is maybe understanding what I would call dimensionality. If I'm going to make a plot of 1,000 data points, that's not really complicated. I could do that. If I wanted to amp it up to 1,000 by 1,000 data points, all of a sudden I'm dealing with 1,000,000 data points. I'm not sure that I could really do 1,000,000 data points on my Sun, on the workstation. The SGI could do that, but probably not my local desktop. If you go to like 1,000 by 1,000 by 1,000, you're up at 1 billion data points. That is a little tricky to deal with. And in some sense, this is the root of a lot of the problems we had, because we were dealing with the beast. We'll talk more about the beast later. The beast was basically 1,000 workstations. And that size let you solve kind of new problems, but it introduced other constraints, like, me expecting to do things with that data set was not going to work. So this is kind of the setup. You got the beast, you got data, got other things going on. I'm going to leave that behind for a moment and flash forward 4 years to January 1998. So in January 1998, I flew out to Maryland. I actually saw Guido and some of the Python developers out there. And one of the things that I did is I visited NASA Goddard. So this is NASA Goddard, and I gave a talk out there. This was partly coordinated by some of the Space Telescope guys. If you know about the Space Telescope people, they're very big into Python these days, and often talk about this. So this was in sort of 1998, and I remember giving a talk about Python, and one of the people in the talk, they asked this question: how did you get permission to use Python? And it kind of took me back, actually. I didn't quite know how to answer this. Nobody had ever asked this question before. And so my answer at the time is I just said, well, we didn't ask. And that did not go over well. People got angry. Actually, a few people in that talk got angry. They're like, it's like, who are you guys? You didn't ask. What are you talking about? And in preparing this talk, I was sort of going back to that question and thinking, well, why did I answer it that way? And the only thing that I could come up with is that we didn't exist. It was not a matter of permission. It's that we didn't exist. And you can say, you didn't exist. What is that about? So to understand that, you kind of have to understand government funding of big science. In 1992, there was, and kind of in that period, there was a lot of emphasis on sort of grand challenge, high performance computing. This is the so-called Blue Book. It was basically from the presidential budget of 1992. This was something that was given to Congress. Okay, so this is at high level Congress talking about high performance computing. And the kind of thing that you find in there are recommendations for funding. It's like, we think we should fund high performance computing, $638 million. It's like, okay, that's pretty serious. That's, yeah, okay. So and this was like a multi-agency thing. It's like NSF and NASA and DOE and like all these different agencies. So I could see where maybe the NASA people were coming from. It's like $200 million, permission, maybe. Okay, like, yeah, okay. Maybe that's a legitimate question. Like, who gave you permission to do Python on if it's within this framework? But the problem is that we're not in this framework. Let me talk about the framework that we were in. This is Peter Lomdahl. He was a condensed matter physicist. Already red flags should be going up, physics. All right, okay, leave that, hold that thought. So Peter primarily was in a group producing physics papers. That was the primary thing. We wrote lots of papers, physics papers. However, Peter was also the group system administrator. I think he was like a real gearhead. He just loved computers and like fooling around with code and stuff like that. So he was the sysadmin for the group, which was very unusual. Most physics people are not going to be the sysadmin. So he managed the Sun workstations and other stuff. And that meant that he also knew how to set up networks and connections and other things. But this idea of networks is sort of more than just machines. By being a system administrator, he was sort of plugged in to the computing group at the lab, so to speak. There were a lot of people doing computing, like other system admins and other things. And so he had access at sort of a personal level to some very advanced parts of the lab, specifically the advanced computing lab. And the advanced computing lab is where they had things like connection machines. So in 1989, as the lab had a connection machine too. This is what it looks like. And that was sort of set up to sort of as a test bed for doing programming. And then one of the kind of dirty secrets about those machines is that they often sat idle. I asked Peter about this, and it turns out if you wanted to do something on the CM2, it was easy to do that because nobody wanted to program it. It was like really weird to program, had 65,000 processors on it. And like, it's like, basically it was too hard to code. People were using craze. And so he could get access to that without any official approval. It was more like a tolerated access, like, you want to use it, go ahead. So I had access, and by having access, that actually allowed access through various upgrades. At one point, the machine was upgraded to a connection machine 5, and then later to some craze and some other advanced machines. And again, this was all kind of, I wouldn't say under the table, but it wasn't really approved. You know, it was not an official project that Peter was working on here. But one of the things that was kind of going on is, we would produce data sets that the computing division liked. Like, you'd take data sets and then it's like, oh, we could make cool pictures out of that. And then those cool pictures would end up on the covers of newsletters and things. And it's like, oh, it's like, so the computing division's looking good, right? It's like, oh yeah, we're doing this great stuff on this machine, look at these pictures. But we didn't have funding. I mean, Peter did not have funding to do a software project. Essentially the funding for any of this, it was more of a side project to a material science project. We were supposed to be studying dislocations in materials. And even that was kind of a side project. That was funded under something known as an LDRD grant, which in tech terms, this might be like a 20% project. Like, sometimes you hear about tech companies and you have like your 20% spare time, you get to do what you want. LDRD was kind of like that, except that you could get a little bit of funding for it. Like, you could submit a proposal saying, hey, I want to work on this thing. And if it got approved, you get a little bit of money. But this whole thing was like a side project to a side project using somebody else's computer that we didn't pay for. And I don't know, they just kind of liked us and so forth. So this is kind of the framework that was in play, is sort of Peter Lomdahl. I entered the picture of this as a grad student. So I was a grad student at the time. Peter and I did most of the coding. I was primarily doing coding. My sort of entry to this was through the student programs at the lab. The lab hired thousands of summer students to do various things, and I came out of that. Peter actually later admitted to me that he was sort of reluctant to have a student. Like it was sort of forced on him. He's like, I don't really want a summer student. And like people, you know, people in the group are like, nah, you should take a summer student. We got all these thousands of students. They got to do something. He's like, okay, I'll pick a summer student. And it turns out I had already been a summer student before. I had worked on some software to do radiation safety training of all things. And that was written in Modula 2. And Peter actually told me later, he's like, the reason I called you is that you were the only summer student who didn't list Fortran as a skill that you knew. And he's like, I just hated Fortran. He's like, no, Modula 2, I'm going to call the Modula 2 guy. So I kind of ended up in this group sort of out of the blue with this weird Modula 2 background, just because Peter didn't want to do Fortran. And so we kind of worked together. Some other people in the group, we had a bunch of postdocs, Niels, Tim, Suja, Pablo. These were physics postdocs, fairly independent. I would say that they kind of sat near Peter, would be their main kind of claim to fame here. Okay, so, but we interacted with them. It's like, you know, interacted with postdocs. And then we had some other interactions across the lab, mostly with like computational chemistry physics. The leader of this whole show was Alan Bishop. This was kind of group director. He was very hands-off. He was one of these guys where it's like, I guess we should have a group meeting once a year. Oh, okay, once a year group, reluctantly. It's like, so he was very hands-off. He basically left Peter alone. There was kind of he sort of tolerated what Peter was doing. He's like, he didn't quite understand it, maybe, but he's like, I see what you guys are doing. It looks good. I'll just kind of let you do what you want, and I'll protect you in a way. So I think Alan, in some sense, was maybe kind of a protector of what was going on, but this was not what I would call kind of like a really well-organized effort. So in answering that question to NASA, you know, permission, it's like, what are you talking about permission? This is like a side project with two people. There's no permission here. I mean, this thing doesn't even exist in any kind of reality. There's like, you know, no funding for software and so forth. So I kind of go into this because I think this is also kind of mirrors how Python was created. If you look at the history of Python, it was never funded. It's like Guido started as like a Christmas break project, kind of on his own, and it sort of existed inside the scope of other projects. They had a big ceremony for Guido about 2 years ago, celebrating the 30 years of Python. I was at that. And it sounded like Guido was almost like a rogue agent. He just kind of went off and made this programming language, and like his supervisor was on sabbatical or something. It's just like permission. I mean, it's like permission is not, I would not say it's part of Python's DNA to ask permission. Okay, so we fit like right into that, you know, permission. Okay, so that is kind of the framework that we're operating in. Is that now I'm going to talk about some other things that were going on at this time. March 1994. The beast. What am I talking about? The beast here. Okay, the beast. The beast in this project was the Connection Machine 5. Very cool looking machine. There's a video of it in operation. Lots of blinking lights. It's all black. Cool shape. It's like, oh yeah, it's awesome. It was sort of punishing to program. I mean, just what we're talking about here is it's a 1,000 processor machine. Each processor had 32 gig of RAM, did about 128 gigaflops, had 500 gig of disk storage. I'm a little bit, I look at that, I'm like, that's just crazy, because I was taunting my kids 2 years ago, walking around with my phone going like, hey, 512 gig on my iPhone. And the kids hate it. So, you know, 500 gig of storage, but this is what you could get for $30 million in 1992 was that. It was sort of weird to program. It had vector units and a lot of SIMD stuff. You could program it in Fortran and hope that it and just sort of hope for the best. You could also program it in C, but honestly, a lot of people programmed it in assembler, like Fortran plus assembly or C plus assembly. If you got into that, you had to read these like very sort of dense books. I actually have one here, the Connection Machine Vector Unit Processing Guide here, you know, like the kind of stuff that you'd find in there were like memory maps and other things, and you'd have to program it in kind of a mix of assembler and C macros. It's just terrible, you know. So not fun to program, but that's how you got performance out of it. And as a, you know, as sort of a story on that, we were not the only ones kind of playing around with assembly. I remember going to the Connection Machine 5 user group meeting, maybe in '93. A few hundred people showed up for that. I remember some physics, you know, another physics person working on quantum chromodynamics got up and said, yeah, I wrote 20,000 lines of assembly code for the Connection Machine. And everybody in the audience just was horrified. They're like, you're a lunatic. You're crazy. And then, you know, it was like everybody was shocked. But then what, you know, sort of after that guy talked, Larry Smarr from NCSA of the web browser, you know, NCSA got up and did a demo of Mosaic. It was one of the first demos of Mosaic. And like everybody thought Mosaic was like so cool. They forgot about the assembly guy. It was like, oh, okay, whatever. Oh, the Mosaic, we want to find out more about that. So that is, you know, what was going on there. Another thing that was going on, and this is really going to be kind of weird, is that there was a very big focus on performance. Like we really wanted to push the envelope on this machine. Like how fast can we make this machine work? At the time, I was taking computer architecture at UNM, New Mexico, and I was working on a project. I'd written like a cache simulator, and I was trying to figure out how to do better cache performance or something. This is a diagram from that. I remember going to class one day, and I come back from class, and Peter's like, "Hey, I was on the news."
For cars,
here he is on the news. Let me just play it for a second.
Computer chips, materials of all kinds.
I see us being able to
that's Peter, by the way.
Into areas where we haven't even dreamt about, you know, using computers before. That's really what our facility.
Okay, let me pause that for a second. So I come back from class, and Peter's like, "Yeah, it was on the news." I was like, "Oh, interesting. What news were you on?" He's like, he couldn't remember. He's like, "I think it was like CBN or something." I was like, "CBS?" I'm like, no, not CBS. I'm like, "Oh, okay, I don't know." It sounded kind of weird. And on a hunch, I actually called a friend. I don't know whether I recorded this or not, but we set a timer to record this on the videotape. I mean, this is again '94, right? So this video that you're watching is off videotape from kind of me calling somebody on a whim and then ending up with it. So let me play it for a little bit longer.
To respond to those challenges and drive those new environments to allow us to solve those problems in ways we couldn't do before.
Science is moving ahead so quickly that even the top scientists here at Los Alamos National Laboratory tell us they have to constantly adjust to the latest developments in science. The question is, how well can the general public adjust to those same developments as they enter everyday life? Reporting from Los Alamos, New Mexico, I'm Galen Tethrow, CBN News.
It's mind-boggling, isn't it?
Now, I have to pause this for a second and say that this particular newscast caused a certain amount of amusement at the lab. If you know about the 700 Club in the US, this is basically a televangelist program. Pat Robertson, he was like presidential candidate at one point. So Peter ended up on this program, and if you go to the YouTube link, you can see more. But one of the things that kind of ended up with that, this is amazing, is there was the supercomputing fact sheet that came out about the Los Alamos show. The supercomputers, how will you change their life? And in the fact sheet, it talks about the beast. This is why it was called the Beast. We had this. So Pete, I don't know how long we gave Peter lots of like flack about this, like ribbing about this interview. But the CM5 being called the Beast just sort of seemed totally appropriate given all the assembly language and the horrible programming and other stuff. And then in a really weird turn of events, it turns out that the code for us that had the assembly in it was in a file with 666 lines. It is weird. It's like, how does this actually happen in reality? Anyway, the beast, the connection machine 5, was something, you know, for the most part, people, you know, demanded respect, right? You know, it's like, okay, kind of hard to program. You got to program it in real programming languages like Fortran or assembly or C or something like that. And needless to say, people were not happy when I put Python on it a couple of years later. At one point, we were running the Python REPL on this machine on 512 processors, and people found out about it. And they were actually kind of angry. Like they were like, "You're running the REPL. I'm the interactive REPL on half of the connection machine, just like sitting there." I think the beast was fine with it, but some of the people counting dollars were sort of like, we don't know whether it was like that. So anyway, that's the beast. Now, in understanding that last slide, how did we even end up putting Python on this thing? I mean, it's sort of an unlikely turn of events, right? It's like Python, this language created by Guido on Christmas vacation, named after Monty Python, ending up on the bees. Like, how does that happen? Okay, so this question of how to find Python. We basically found it through some popular publications. So one of the publications of that time was Computers and Physics. This is a picture of Computers and Physics. I actually have that here, the same issue. That's actually our work on the cover. That's a picture that we made in 1993, Peter and I, from even before this, you know, kind of the early stages of that. So we had a cover photograph on Computers and Physics. Turns out in Computers and Physics, there was a column, scientific programming, where you'd find things like this, like how to write nearly portable Fortran programs. Okay, well, maybe that one didn't quite appeal to us. You know, yeah, you're on your own with that. But the editor of this column was somebody named Paul Dubois at Lawrence Livermore National Laboratory, actually a competitor to us at Los Alamos, right? Okay, so Paul Dubois. And Paul was very much had his finger on the pulse of a lot of programming topics. He was very interested in scientific programming, and he would often write about new things coming out. In fact, in the same issue where he had the cover, Paul had a little, you know, he has like a little commentary, and he's saying, hey, we're going to learn Perl next time. 1993. It's like, I'll bring you up to speed on Perl. Excellent, Perl. I'm actually kind of glad that Paul was maybe not more successful in that, you know. Maybe we would all be doing this conference in Perl if he had. But Paul was actually talking about a lot of stuff related to programming. One of the common themes about what Paul was talking about was the idea of making programs programmable, or making physics applications programmable. So this is an article from 1994 in the same magazine, and he writes about this vision. Imagine writing physics codes in Fortran. Okay, you have to forgive that a little bit, but controlling them with something else, some kind of high level thing, right? Like a high level programming language where you can create variables and loops and so forth. And this is 1994. This is exactly the kind of thing we're doing with Python now. All these extensions like NumPy, they're written in C, we're controlling it from Python. So he was talking about this in 94. And I learned about Python through that column. This is January 1996, and it's maybe one of the earliest, one of the earliest mentions of Python I could find, but it was just in a blurb. It was in his like little commentary up on the side. It's like Python 1.3 has been released, and then it had this description of you can do C extensions and dynamically load it. And you can embed it. And I was like, oh, that sounds really awesome to me, because I was actually working on a different project at that time called Swig. Some of you may have encountered Swig. Swig had not been out all that long, but it was something I was already working on in another context. I was like, ooh, Python, what's that? Oh, that sounds cool. So a couple months after this showed up, that's when Python got added to the to the so-called SWIG project. Now, whether it was good or not, I don't know. I mean, you can see my commentation down here about, oh, it's a kludge, and like I might have to rewrite it or something. But this is where it showed up. Some other things that are happening at this time, May of that same year, 96, is when numeric Python actually got written about. This is the predecessor to NumPy and some of the other extensions, Paul Dubois and Conrad Hinson and James Huguenin and some people in that same magazine talking about, the numeric part of Python. And they are talking about the earlier article, the 1994 article, saying, hey, Python is really well suited for this programmable physics idea. It's a scripting language. You can bring compiled code into it. This is great. Now we're doing numerics. Okay, so that was going on. And then in June of 96, you had the 4th International Python Conference, which was held at Lawrence Livermore National Labs. This is in Paul Dubois' backyard. And so you had the 4th International Python Conference, a small conference, about 50 people. I was at that. It was maybe 50 people. It was actually behind the fence at Lawrence Livermore, meaning it was like in a secure area, and it required like background checks and all this stuff. And we actually got a big tour of the laser facility out there. It was crazy, but that conference had a number of talks about science with Python, like scientific graphics package for Python with graphics, more graphics, visualization, Python with numeric Python in physics and stuff. So these ideas were really front and center at this conference. There were some web programmers there too, so it was a real weird mix of like web programmers and physics people. But that conference really set up a lot of themes about what people were thinking about: graphics, visualization, data analysis, problem solving in science. One thing at this time, I'll just mention it. There was no interest really in programming per se. Like the topic was not really Python as a programming language. It was more like, oh, how can we use Python to do this other stuff, like visualization? That's what we want to do. It's that. So if anything, this maybe would be a precursor to like Jupyter notebooks or something. It's like, yeah, we want to solve all these problems. So that was what was going on in 96. Now, I had just mentioned that I was working on this SWIG project, and it's. I want to say a little bit more about that. I have to back up a year to get into that, to June 1995. In June 1995, I had just finished my first year of graduate school, and I came back to work with Peter, and Peter had sort of entered, I don't know, a stage of doom. And by doom, I mean Doom 2, the video game, Doom 2. As it turns out, Peter was I don't know, he was going through some personal things that summer. I mean, like many of us do sometimes, it's like that happens. And for whatever reason, Peter was just like, Dave, just do whatever you want. I'm kind of checking out for the summer, and honestly, it's like his door was closed a lot. And when the door was closed, he was playing Doom 2 in the office. Okay, so I was like, okay, fine, Peter, you playing Doom 2. I actually could not really blame him that much, because I had just spent like the previous 2 months playing Marathon on the Mac, trying to avoid thinking about my qualifying exams in graduate school. Okay, so it's like, fine, okay, you want to play Doom 2? That's cool. Okay, so it was kind of a weird summer, Doom 2, video games. Now, going back to my graduate school experience, I, again, was in my first year of graduate school at the University of Utah, and mostly I was taking classes. Okay, I was not doing research, wasn't doing any projects, but I was sort of attached to Chris Johnson, who was a professor at University of Utah, very well known for visualization and other things. And so Chris was working with a graduate student, Steve Parker, on this visualization system called Ski Run. Now, Ski Run was like, the epitome of flashy. I mean, this was something that ran on these SGIs. It was really cool. I mean, it's like you could like rotate, like fly around data and do all these things. It had this big visual programming environment. It was really kind of awesome, actually. I mean, and later on, Chris, like the group actually built this whole kind of thing around ski run, and Chris ended up being my advisor, but I was more of a side project to ski run. Okay, so I kind of worked in this framework, but this is a good example of where that $638 million was going. I mentioned the big funding for computing. That money was basically everywhere. I mean, it was at the universities, it was at the labs, it was over multiple agencies, and projects like that, these like really fancy visualization projects, that just attracted money like crazy. It's like, yeah, we want that. And Los Alamos was, sort of part of that too. I mean, we had a lot of very fancy hardware, like expensive silicon graphics machines. They actually had like little signs on it because they would often bring like tour groups in there, like, oh, let's bring some high school kids into the computing centers. Like, ooh, silicon graphics. And then, they do these demos and all this stuff. It's like, oh, yeah, awesome. Okay. So we had machines with like lots of demos. These were sort of hooked up to supercomputers using very expensive networking. Like Los Alamos developed its own network, like high-speed interconnect to connect supercomputers and build like whole creative supercomputers and other things around that. There was also kind of an emphasis on the software side. Let's do object-oriented programming, C++, big software kinds of projects. And so the $600 million was all around. People doing big computing kinds of things. And so one sort of weird thing about this is just how did it intersect with us? Okay, keep in mind, we got Peter, condensed matter physics. And it didn't really intersect with us directly at all. This is more how it intersected. We had certain collaborators at the lab. To protect their identity, I'm going to call one of them Pinky. It's not their real name. But we would kind of collaborate and eat lunch with Pinky. And then like I would join Pinky for lunch as well, because what am I going to do? So we'd go to lunch. And then, Pinky, as it turns out, was married to Mabel, who sort of worked over in the applied physics division as an application programmer. And Mabel also would sometimes come to lunch, and kind of fill us in what's going on over in applied physics. And so she was, kind of a user of the C++ for scientific computing crowd, sort of the big project over in applied physics. And we got sort of a lot of inside information about how well that was going. And it was usually things like, yeah, it's some kind of template hell and it doesn't compile and we can't debug it with anything except print. And everybody hates it. It's like, oh, it's just constant horror stories coming out of this project. And so again, we weren't really involved with that, but we kind of looked at that and it was like, wow, I mean, I don't know what they're doing, but we definitely don't want to do that. It's got to be some better, better way to do that. So, we were sort of exposed to a lot of these things, but in some sense, we wanted to go against the grain a little bit. And so that was going on. Just as an aside, by the way, if you flash forward several years later, it turns out that some very important individual, who I'm going to call Buffy, not their real name, over in applied physics, in charge of this thing. Oh, also, by the way, applied physics at Los Alamos is a euphemism for nukes. I'm not going to sugarcoat that. So this was coming out of a certain division of Los Alamos. Okay, Buffy was in charge of that. Heard about what we were doing with the Python stuff, and he's like, okay, let's have a meeting. Buffy and Peter have a meeting. As part of that, it was sort of found out that we didn't have any funding. This whole thing was like a side project to a side project. And the story, as I understand it from Peter, is that as part of that meeting, he found out that Buffy actually really kind of liked the Python stuff. It's like, wow, that's really cool what you're doing. Here's some monopoly money. Actually, literal monopoly money handed to Peter, who was then told, give it to my secretary on the way out the door. And it showed up as funding to keep supporting some of the molecular dynamics work. So trying to figure out like it's like that comment about this not existing as a project is like, it's crazy. It's like a side project to a side project that's now liked by somebody with just throwing money around out of the applied physics division. It's like, wow, okay, crazy. But ignoring that, it's like, okay, it's like what was I talking about here? June 1995. Okay, I got to back up to June 1995. I'm kind of sitting in this situation thinking, wow, this is really great. Everything that's going on. It's like Peter wanting to play Doom, everything broken, everyone wanting to do C++ and like that stuff. It's like, so it's like, you know, what am I going to do for this project? And Peter basically saying, oh yeah, just do whatever you want. I don't know, just leave me alone. Go, I don't know, go do whatever you want. So coming out of graduate school, I had learned certain topics. I took a course on compilers. That was pretty cool. I took some systems stuff, operating systems, networks, systems programming. I'd taken a class on ML program. This is not machine learning, by the way. This is the ML programming language, which is very advanced type systems, functional programming kind of things. And I was thinking about all that stuff. It was like, what am I going to do with all of that? And this summer, and I was like, you know what I'm going to do? I'm going to blow up StirToke and get on. You're like, StirToke, get up. What is that about? So it turns out these physics codes were almost always these batch processing jobs. You control it with a script. This is how we controlled our code in like 1994. Looked like that. It was terrible. I was like, I got to get rid of that. So what I wanted to do was just get rid of the batch processing stuff and put a scripting interface on it. And I ended up doing that. I wrote a scripting language for the physics code that was kind of my own creation. Now, part of the reason for doing this is that the connection machine was just such a weird machine that you basically could not port code to it. I mean, it's like if you wanted to use it, you had to write it. And I was like, okay, I'll write a scripting language. Did I care about programming languages? No, I did not care about making a programming language. It's like what I was trying to do was this. I wanted a scripting interface so I could take my physics code and then add some components to it, like visualization and debugging and some other stuff. This is exactly the thing that Paul Dubois was talking about a year earlier in the computers and physics. I was not aware of that at the time, by the way. If I had, I probably maybe would have changed what I had done, but sort of the same idea, kind of controlling things with scripting. And really what I was trying to do is just kill the whole right-hand side of that diagram. It's like, I didn't want to deal with the data files and the SGI and the FTP and all that stuff. It was like, enough of that. I want to do something else with that. So that was the vision. I ended up abandoning it when I came back to graduate school because I told them, hey, I wrote a programming language. And then they were immediately like, no, you didn't. Forget about that idea right now. That's not happening. So, okay. So then it turns out there were other stuff out there like TickleTK and Perl, and then I found Python, and Python was great. I mean, we liked the syntax of it. The REPL sold it. It's like, oh yeah, the REPL, I want that. Definitely want that. You could interface it with C code using, Swig and some other things. And then the other thing is the implementation was pretty clean. It was written in C, had few dependencies, and one thing that we were really into is we wanted to be able to hack it. We found it something that you could hack. And by hacking, it meant that you could put it on the connection machine with a bit of work. And so that was really, that's really what we saw on it. I think there was something else kind of in play though. And I think this is something that Paul Dubois really had some insight on as well, which is it would be much more powerful to be involved with a community of tool builders than just to make your own custom tool off on the side. And I agree with that. I mean, I think one of the things that we kind of saw in Python is that Python could serve as kind of a common glue for building a lot of stuff. And then if people gave it away, you'd be able to use that, right? It's like, and you could also sell it a little bit better, right? Because it's like, oh, we're not making our own programming language, we're doing Python. It's like a tool. So I think that was useful. And just as an example of some of the tool building, I thought I would talk about the visualization system that we made for this thing. was very much kind of a do-it-yourself attitude. That was one of the goals of being able to do this. It's like, oh, physics people, you can make your own tools. And so we were kind of operating with some constraints. I mean, basically every node of this parallel computer was a 32 megabyte machine. And we were trying to basically embed visualization and scripting into it. And we were very concerned about kind of the efficiency of this and doing it very cheaply and not having a lot of code. And so we built this visualization system, and here's what it looked like. This might blow your mind. One of the tools that we used on the workstation was this image viewer called XV. I don't know if anybody uses that now. It's probably really dated, but it was like this great kind of image tool. So we took that, we had the source code for XV, and I ripped out the GIF encoder out of XV and I put it into the physics code, just doing cut and paste of C code. So I took the GIF encoder and put it into physics. As an aside, the compression algorithm in GIF at that time was the subject of patent litigation. And I knew that, but I kind of figured if they want to come out after a lab with nuclear weapons, they can do that. Okay, maybe I don't know. Maybe not. Okay, so we kept the compression around. I had written a graphics library as part of the radiation safety project from 1990. So I still had that code. So I took that and kind of adapted it to the connection machine. And then using some system stuff, we hooked it up with sockets and built this like image server thing that would feed XV. So like a whole lot of pieces kind of slapped together. There's actually not a whole lot of code there, but it was just sort of glued together stuff. And then we took some code from the computing division that had previously been on the SGI and kind of adapted it, and then slapped a scripting interface on it, and then tied the whole thing together. And it was awesome. I mean, it was sort of hacked together, but what used to take hours was reduced down to like 2 seconds. And it just blew people's mind. This is what it looked like. Not real fancy, but you would essentially do a lot of like terminal windows with XV displays sort of shown. And then it kind of operated in the same way that people might use like a Jupyter notebook in a way. You know, it's like interactive computing, and you could like do plots and see things and so forth. You could also, at one point, one of the postdocs, he was like, hey, is there some way I can monitor the code on the supercomputer while it's running? I was like, yeah, I'll put a web browser in it. So I used Python's web browser module just to open up a socket on one of the connection machine nodes, and then he was able to access that at home over a modem and then see like images coming off the connection machine. I don't think the computing division ever knew that we had an open network port on the supercomputer that was accessible just to the outside world. So times are different there. Just to give an idea of like how effective this was. This is sort of an unusual story as well. So I was back at the University of Utah, and at Utah, somebody had decided that 3 times T1 is equal to T3, as it obviously is by the math. And in doing that math, they kind of observed that if that's true, why is T3 costing $45,000 a month? We should get rid of T3. That's stupid. Why would we pay for T3 when we can have T1, 3 times T1? Not realizing that these were actually network connections of different bandwidths. At that time, a T3 connection was a 45 megabit per second connection, whereas one was a 4.5 megabit connection. University of Utah actually got rid of their 45 megabit network connection and put the entire university of 28,000 students on a 4.5 megabit internet connection. And the bandwidth just dropped off the cliff when that happened. But one of the things that happened is my little visualization system with the GIF files worked great. It was like, yeah, I can still access Los Alamos and I can still do these visualizations. And it blew people's minds. They're like, wow, even though this completely is terrible, it still works. As a funny postscript to that, it took the university 6 months to get their internet connection back because the provider gave it to somebody else. And to get a new connection, they had to run fiber from Cheyenne, Wyoming, which is about 400 miles away. we had to wait 6 months for it. So truly terrible situation. On the Los Alamos side, this system led to a lot of papers. That's what we wanted to do anyway, was write physics papers, and it really enabled people to do that. So it was pretty awesome to kind of see this system kind of in play. This is kind of a random note, but the molecular dynamics software was later adapted to study pandemics, specifically the H1N1 swine flu or whatever that was from like 2005. And I actually saw it on the news in the last year when they had that whole thing about the pandemic, like simulation. Like, I don't know, everybody was like dunking on these these pandemic researchers. There was part of me, it's like, oh, please God, let that not be our code. I do not. Thankfully, it was not us. You know, I thought, God, that would have been terrible. But the molecular code actually got adapted to that, believe it or not. So anyway, this story, we're almost at the end here. This definitely was not just us. If you look at a lot of the origin stories of things in Python, it's kind of a similar story. This is from the 6th Python conference, 1997, Conrad Hinson, talking about molecular modeling. If you read about that, it's kind of a similar story. It's like, here's a tool written by a single person over a year, part-time. I don't think he asked permission, and I don't know whether he had much funding. I mean, it sounds like a part-time project. Same thing with some of the tools we use now, IPython. I was a grad student using Python. Don't think he asked permission. I don't doubt he had funding for this. It sounds like, it's like, this is just something cool I want to work on. And that's what I'm doing. So a lot of stuff like this kind of in this time period, it's like people, kind of doing things on the side, almost no funding, no permission or anything. And there's a lot of stories that are kind of similar to that. So Now, to kind of wrap this up, I'm looking at the clock near the end here. I want to talk about some lies that we used to tell people in working on this stuff. First of all, Python was not something that people were into. Like, if you had to sell this to higher up, they're like, no, what are you doing? And there were all sorts of things that would be told, like, it's a prototype, or it's throwaway code, or we'll rewrite it. Yeah, we'll rewrite it in C++. Or it's optional. Yeah, it's optional. The optional thing is actually one of the things that we did in our project, because what we tried to do is we're like, yeah, you get rid of the batch processing and you put this scripting interface on it. And it's basically the same. And this tool that I had written called Swig was kind of part of that, where it would take like C header files and then just build like a Python interface from it. We would tell people, oh, just use that. And the whole reason it was released was actually with the hope of subverting other science projects to do scripting. We thought scripting was great. We're like, oh man, we could really mess up these projects by providing like an open source tool to let them do what we were doing. And so that was kind of some of the motivation for that, to, I don't know, infect other projects as well. Another strategy that was kind of also in play is you would tell people that others were doing it. This is something that Paul Dubois did, actually. This is sort of interesting to see, but Paul invited me out to Livermore in July 1996 and had me give a talk about steering physics codes at Los Alamos. And the pitch that I gave at Los Alamos was basically what I just described. Actually, I'll play this. You can listen for a minute here. I'll talk about it.
So one of the ways, the way that we, or at least the way we approach this, is we started playing around with scripting languages last year. And the idea was we would take our original molecular dynamics code, shown over here on the left, and what we would do is we would add sort of a scripting language to the front of it for controlling it. So the way that worked is we basically took our original application, put this new front end on it that was an interpreted language. And then once we had that, we started adding new modules. So we added some things to do data analysis. We added some things to do visualization. We added some networking code to send information back to a user's workstation. And kind of the idea was you'd leave the original molecular dynamics code about the same.
Okay, leave the code the same. That was probably the big message. It's like we're trying to corrupt people. It's like, hey, you could do the scripting stuff and leave it the same, but do all this other stuff. The reason that this talk even exists is Paul Dubois was in the audience. He had me come out there, and I think what his purpose was to tell the Livermore people, look at the Los Alamos people, because Livermore and Los Alamos kind of enemies of each other, right? Like, oh, look what they're doing. Well, how come we're not doing that? I don't actually know whether Paul understood that it was just like two people doing it on a side project. I mean, maybe he did, but it was not presented in that way when we were out there. So maybe, I don't know, maybe it's like a propaganda piece or something. Okay, so so that is kind of at the end of the talk here. Now, some things that I kind of think about. Okay, getting to the end. Python has really kind of is ascendant right now. Python is #1. Go Python. All right, good. You know, and I think about, you know, where Python is right now. But I also think about this story. I mean, this story that I described, this is 26 years ago. And if I go back 26 years and I look at things like C programming, it was only 23 years old. C was from 1972. Python right now is 31 years old. Maybe you've seen this XKCD about the environments, right? You know, and it's like, I look at Python, it's like, huh. I think about, you know, what's going on with Python, and I think about the future of what's happening with Python. But instead of thinking about the future of Python, I sort of wonder whether there's a successor to Python. And I honestly don't know. But if you think about this, you know, this story, I mean, and what we ended up building in some sense was a successor to C and to Fortran and a bunch of tools. I mean, we didn't totally give up those tools, but we're, you know, thinking about like a different approach. So I think about this future, and I think about, you know, this question: is history something that repeats itself? Are we in a situation, you know, is there, you know, is something going to emerge out of this? Is there stuff going on? Are there students and postdocs working on new stuff right now? And if they are, what are they studying? And what problems are they solving that are different than what we're doing? Are they doing something better than what we're doing right now? And who's providing the environment for doing that? And who's getting the word out? I mean, a lot of these things kind of went together, you know, and you know, I see in the chat somebody commenting about Julia. So maybe it is. I don't know. I don't have any particular thoughts about any specific thing, but I think about these kinds of questions and how Python kind of took over the science world, kind of, you know, through different means there. And so those are questions to think about, and I think they're worth thinking about for other people as well. So that's the end of the talk. You know, admittedly went a little over a few minutes that I'd hoped there, but I'll see if there's some questions that people want to ask. And
yeah, David, thank you very much for your interesting talk. We don't have any questions in the Q&A just yet. We have about 2 more minutes. So if there's anyone with a question, you can ask it in the Q&A.
Okay.
So hoping for some extra questions. Again, thank you very much for your talk, David. It was very, very interesting. And I see Isaiah also asked, what would you do differently in Swig today? Have you talked about that anyway?
Oh God, differently in Swig. I have no idea. I mean, maybe this is going to be this is going to be a really bad answer, but I have like so much post-traumatic stress from C++ that maybe I wouldn't do that the second time around. Although I'm not, you know, maybe Swig would not have been successful at all if it hadn't done C++ in the.
All right, I think that's all we have time for. So thank you very much again, David, and thank you for being here. And I hope for all the participants that they enjoy the rest of the conference.
Okay, thank you.